All right, guys, so this is the start of basically a new unit, which would have started earlier this morning. What we're going to actually look at is with derivatives. We're still looking at derivatives, but we want to be able to we want to get to our like slopes of tangents much faster than using first principles, okay? And so there must be a better way, right? And so that's what we're going to spend this unit on is finding the slopes of tangent lines in the most efficient way possible. Okay, the important part is though that you guys realize that these things, these shortcuts would not be possible without the use of first principles. Okay, and so every one of these laws that I show you this week could be proven using first principles. Okay, and if you guys are interested in looking those up, you can. What I'll do today is show you this one, and then I'll just tell you what the rules are from this point forward from the interest of time, okay? But it's imperative even for you guys to realize that this stuff comes from first principles. They're not just magic, okay? And so I'll show you how that works today. But first, let's do an example where we actually derive a function like x cubed. Okay, we'll find what the derivative of x cubed is using first principles, and then we'll compare it against the actual application of the power law that I show you today. Okay, so first things first, why don't we jump up here and we'll find, right, we know that f prime of x, we're going to use first principles, so we know f prime of x is equal to the limit as h approaches 0 of x plus h minus f of x. Oops, there's an f out there, and divided by h. Okay, so let's find what these things are, right? X plus h, f of x plus h is going to equal x plus h cubed. Okay, and we're going to leave a little space there for a second. Okay, let me move this over. And we know that f of x is just equal to x cubed. Now, this here is the same as, I'll save you some time, x plus h times x plus h times x plus h. And if you were to expand this out, right, what I'll do is I'll scroll down here so you guys can have a look. If you were to expand this out, here you are, x plus h. If you were to start to do binomial expansion one at a time, you would see this procession of math, okay? And then you'll start seeing, okay, well, I could combine this, the 2x squared h with an x squared h, and then you could combine the xh squared with an 2xh squared, and this is your final result, okay, after the expansion. So what I'll do is I'll grab this, and we'll bring it back up here. Okay, we'll drop it in here. Might have to shrink it down a little bit. Okay, but that's where it comes from. And now we can take that and we can actually find f prime of x, right? We know that that's the limit as h approaches 0, right? And we're going to plug this in. So x plus, x cubed plus 3x squared h plus 3xh squared plus h cubed minus, don't forget to subtract off the original function, x cubed, divided by h. Okay, and then you'll see h cubed creates a zero pair with the minus h cubed, and conveniently each one of these three terms here has an h term in it. Right, so we can factor that out, and that becomes our next line. F prime of x is equal to the limit, getting sloppy here, the limit as h approaches 0 of h times 3x squared plus 3xh plus h squared, all divided by h. And then at this stage, if I were to actually evaluate this limit by plugging in h approaches 0, you'll find that f prime of x is equal to 3x squared. So there is your derivative, or what we called our slope of the tangent. Sorry, I'm just looking at this. I don't know where this came from here. I don't know what that was. Okay, so the power law for derivatives. Okay, we need to recall some proofs or identities. Okay, so we'll write a squared minus b squared. We could rewrite this as just a difference of squares, right? So this is going to be a minus b multiplied against a plus b. Okay, and then a cubed minus b cubed. I think we've seen this one already. A minus b out front. And then we say a squared plus ab plus b squared, right? A to the 4 would be something like this, and hopefully by the time we get to this stage, you guys are starting to see a bit of a pattern. A cubed plus a squared b plus ab squared plus b cubed. Okay, and if we kept going, we would see this pattern continue to repeat itself, right? Right between each of these. And if I was to write this generally in terms of n's, right, we're going to write a minus b out front, right? But then our first term is going to be a n minus 1, right, plus a n minus 2 b, a n minus 3 b2, b squared, sorry, not b2, plus, and we continue, and then we eventually see it come back down, minus 3 oh, I wrote that one twice. Oh no, I'm okay. One sec, sorry. I had one. 2, A, B, and then we lose the A, and we're just left with B to the n minus 1. Okay, and so what we're going to actually do is for any function or any function, x to the power of n, okay, we can apply what we call the power law, right? This is where we're going to produce the power law proof. Okay, so we can see that, you know, we're going to use this last one here to help us here. Okay, so the limit as h approaches 0, we're going to have x plus h to the power of n minus x of n, the original function. Okay, that's what's going to go on the line. Now, we have a situation like this right here, right? So we're going to try and rewrite this, but with our function specifically in there, right? Our function of x to the n. Okay, and so that's what we're going to write here. So we write a minus b. Well, a is the first part here, and b will be the second part, right? This x to the, well, just the x to the power of n. But a is going to be the x plus h piece, right? So what goes on this line is we say, okay, x plus h, that's our a, minus our b piece, which is x. And then we open up another bracket, right? This is going to be all this stuff now, right? Just written in terms of our specific function here, right? So we're going to have x plus h n minus 1 plus x plus h n minus 2 times x to the power of 1 plus x squared plus dot dot dot, and then we go the rest of the way. Oh, I'm getting carried away. We'll go back into B mode here. X to the n minus 3. That's not an n minus 2, that's the squared, right? and plus x plus h to the power of 1, right? That's this one here. And then we're going to have x to the n minus 2. And finally, here I'll try to move this over or shrink it or something. Finish this off. Plus x to the n minus 1. Okay, what you'll see right off the top, if we were to actually what we'll call collect like terms in this first bracket, you're going to see that the x creates a zero pair with the minus x. And what you're left with, conveniently, is h, right? H times all of this stuff. And I'm just going to copy paste this for the interest of time. Okay, and then you'll see the h's cancel or create like a, well, they cancel one another, create a 1, right? And then underneath here, we're going to actually, at the same time, in the same line, we're going to actually evaluate what the function goes to, or when we evaluate when h approaches 0, right? So we're going to replace all these h's with the limit h of 0. And what are we going to be left with? Well, we're going to be left with x to the n minus 1 plus x to the n minus 2 times x plus x to the n minus 3 times x squared plus, and then we start coming back down. Okay, so we're going to say x squared times x to the n minus 3, oops, plus x, it's hard to keep track of, x to the power of 1 times x to the n minus 2 plus x to the n minus 1. They're very easy to get lost in these things, and I don't want you guys to lose track of what the important thing is actually applying these, which I'll show you how to do after. But the important part is that we're able to actually use our first principles to prove what it is that we're actually going to use. Okay? Now, as long as you're okay, like we've taken an identity up here and applied it to a particular scenario, in this case x to the power of n, right? Now there's something else we can do here, right? And this is kind of, I think, the cool part of the entire question, right? Or the entire proof. You know, we have this x minus n, x to the power of n minus 1 on both ends here. Now, wouldn't it be something if I took this here, and you guys know with your power law rules, right? We're going to have to add the exponents. Well, we have a 1 there. So we're going to have x to the n minus 2 plus 1. Well, that turns into x to the n minus 1. Well, what about here? X to the n minus 3. Well, we're going to add the exponents, right? Plus 2. Well, that turns into the xn minus 1. And you'll find it does the same thing across the whole way, right? How many of them are there is the question, right? That's the last part. So you're going to, down here, you're going to say, we'll ignore this for a sec. We're going to have x to the n minus 1 plus x to the n minus 1 right? How many of these do we have? We have n of them. So that would mean that I could factor it out, right? And write it out front. Well, we have n times the x, the n minus 1. That is the proof, right? And so we can say if f of x equals x to the n, then f prime of x will equal n to the x and minus 1. This is your power law rule that you will use. And the simplest of them all, but nonetheless, it gives us a starting point, right? Right? We can also see that if this was a constant, we would get a f prime of x would equal 0. Okay, that's important to note as well. Okay, so what I want to do here is I'll show you this. Okay, and then I'll hit pause, and then we'll just do some examples, and then that'll be pretty much. Well, we might power through this. No, I'll hit pause. We'll have two parts. Okay, so let me just prove to you that this actually works. We saw what the result was up above using first principles. There's the result we're expecting. Okay, if I was to actually come down here and apply this rule we've come up with, right, where here's the derivative for power law, okay, well, it tells us to take the exponent. This is how it works. Much easier than the actual proof. Okay, we're going to take the exponent. It's going to come down out front. Okay, but then it tells us to take, in this instance, n, I suppose I'll write this, n is equal to 3 here, right? Y is equal to 3 because the exponent is 3. So what's it tell us to do? Well, it tells us to take n, multiply by the function, and then take n minus 1 in the exponent, right? So we go, the 3, if I was to rewrite this, exactly what's gone on here. The 3 came down out front, and so we got a 3x. But when you do that, you have to do 3 minus 1, which gives us the 2. That's how we get to there. Okay? This is your power law, right? This is the why it works. Okay? Much easier than, you guys saw, much easier than using first principles. Right? Look at all this work we had to do to get to this answer. And the whole time, if you guys went back and looked at all your first principles work, that's staring you right in the face, right? We bring the exponent down, do an n minus 1 on the top. There's your power law rule for derivatives. Okay? So I'll hit pause there, and then we'll work through some examples, some more complicated examples anyway. And you guys will be experts at applying the power law after that. Okay? So stay tuned for part 2.